So we've just established the following results. We have a theorem now, so prove this. And we have a theorem. Given any circuit computing some function f of x, we showed that we can build a reversible circuit for doing the same task essentially, but the only thing we're going to note, which is going to become important, is that we had to assign some ancilla bits as input in order to do this, right? So what we're really doing when we're doing this out of Fredkin, which is to say when we're doing it reversibly, is we do have whatever the input x is, but we also have some ancilla bits. And then we showed that we can do this reversibly. So I'll use double arrows to indicate whenever we're doing something reversibly today. And what we showed is that we can still evaluate f of x. Why can we do that? It's because this gate is universal, so I can evaluate any function that I want to, right? But what we have in the output, you'll notice, is the thing we want, but some other things, which are a function of the input and potentially the ancilla bits that we had. So we're not very nice to what we call that. We call that garbage bits. So we'll use g to indicate that. And g could be a function of the input x that we have, as well as the values of the ancilla bits. So we call g garbage bits. And so in quantum computing, this would actually cause some problems for us. And so what we're going to ask is if there's a way to do this without any garbage, okay? So the rest of the lecture today will be taking out the garbage. We want to think of a way to do this where we're just mapping the input x to the output f, and then the rest stays more or less the same. So with the ancilla bits, so I'll note this is the ancilla as well. With the ancilla bits, I hope you agree that I can create whatever they are from the 0 state by just using NOT gates, right? And so, for example, I could start all these in the 0 state, and here I would do nothing, and here I would do the NOT gates, okay? And that's going to generally be true. So we know that NOT is reversible. So we can still do this construction, but instead of starting in the ancilla, I can start in the 0 state, and then I'll just add some more NOT gates into the circuit, but NOT is reversible, so I'm allowed to keep the arrow going both ways, being reversible here. So ancilla bits, whatever the values we want can be prepared from the all 0 state with NOT operations, which are reversible. Therefore, we can write it in the following way. Let's do it as x comma 0. Let's put the preparation of the ancilla into the circuit itself, which is this reversible arrow. And then we're outputting the function that we care about. And then the garbage bits will no longer depend on the ancilla because we put those in the circuit. So I'll just write that as g of x now. All right. So the usual way to make something reversible that's not reversible is the trick of making a copy. Okay? So we're going to think about making a copy of the answer that we want into some other register, and then doing the circuit in reverse to get the initial state that we started with. So that will be the trick. We just have to think about how to do a copy reversibly. And in some ways, we've already seen the answer. So let me introduce or define for you again the C NOT gate, the controlled NOT gate. So in the same way that C swap is a controlled swap, C NOT is a controlled NOT. And this gate will have the following effect. C NOT will act on 2 input bits. I'll call them, in this case, C again for the control, and then I'll use T for the target. So with C NOT, we often use this vocabulary, control bits and target bits. And the output of this will be the control bit never changes. And then I'm going to add the control bit to the target bit mod 2 in the second register. Okay, so again, circle plus is addition modulo 2. We've seen this in a quantum circuit. Of course, it's also a valid classical gate. And this is also one that's going to be reversible. Can anyone see why C naught is a reversible gate? Exactly. How could I subtract? Think about addition modulo 2. Exactly right. Would everyone agree that for any input bit x, or let's just think about using C, what is this going to evaluate to? C plus C mod 2 is going to be 0. Because if C is 0, 0 plus 0 is 0. If C is 1, 1 plus 1 is 2, I loop back around to 0. Okay? So C plus C this is going to be 0. So again, with the same trick as the Fredkin gate, if I do this twice, what will happen? I'll get C, and then I'll get target plus C. If I do it again, I'll get C, target plus C plus C. That will be subtracting, so that will take this back to 0. So C naught also is a self-inverse gate, and therefore it's reversible. So if I do 2 of these, we have the theorem. C naught is reversible. So that's great. I'm allowed to use that in this construction, and I can keep the arrow going both ways. Now let's just think about a special case of the C naught gates, which is where the target bit is set to 0. So note that C naught applied to the control with the target bit being 0 will always be the control bit and then the control bit. Does everyone agree? So this is a copy. C naught is making a copy of whatever the control bit is in this case. And it's also reversible, so this is a reversible way of making a copy. Okay? That's going to be very useful in our construction, and that's essentially going to be the secret that we use to get rid of the garbage that we don't want in the circuit. So let me write that down for you. We're asking the question if it's possible to get rid of this g of x, and it is. What I'm going to think about doing is creating some other registers so I can store some additional output. So what we'll do is we'll have x, 2 registers of 0, and then some other bit y, which could either be 0 or 1. We're going to just think about writing the answer, the evaluation of the function f, into this last register, and that will be our output. It could be 0 if you wanted to. I'll just stick with what the textbook does and keep it as a y here. So we'll have y plus f of x mod 2 as the final output. Okay? So we'll start with this, and then what I'm going to do is I'm going to evaluate the let me write one more step before I do this, actually, sorry. So what we'll want is a register where x0 gets mapped to x and f of x. So sometimes you might want to keep around the input as well. So let me think about doing that with C naught first. So what I'll do is I will create x, 0, 0. So let's start in this state with 3 registers now. And then what I'll do is I'll keep one copy of x around. I can make a copy of it to this second one using the C naught, so x, x, 0. And C naught is reversible, so I'm allowed to write the arrow in both ways. Now let's evaluate this reversible circuit. So the second x0, that x0 here, will get mapped to f of x, g of x. So that, again, we argued was reversible. So I have f of x, g of x, using our argument here. Does everyone agree? Okay. And now I'm going to introduce the last register, y, which is where we're now going to make a copy of the output that we want, f of x, before we undo these steps. Okay? So let's copy f of x into a final register, which we'll think about as starting in some state y, which could either be 0 or 1. So the final construction will be x, 0, 0, y as our inputs. I will first evaluate this. We wrote it as 2 steps before, but I'll just write it in 1 here. So this will be x, f of x, g of x, and then the y was just hanging around. Let's call the circuit that does this u, with the understanding that u is reversible. So I'm able to do its inverse, u inverse. Okay. Starting to use this notation because this is leading us into quantum circuits where everything will be unitary and reversible. All right. So we just showed that we can do this construction. And now I'm going to use a C0, which I also know is reversible. And I'm going to write the value of f of x into the output register y using this definition of the C0 gate here. So x won't change. The control is f of x, so that won't change. G of x isn't being touched, so it won't change. And then the last is the target register. So I'll have y plus f of x. Y plus f of x. Does everyone agree? The last thing I'm going to do to get rid of this garbage is just do the inverse of what I started with. Okay? So right now I have g of x here. I want to undo this. When I do that, it's going to undo f of x as well, right? Because that's what u did in the first place. It mapped 0 to f of x. So that was the reason that we made a copy of it with a C0. So when I do u inverse now, I'll still have f of x in this output register. So let's do that. U inverse here will do what? Well, it's just going to map the first 3 registers, x, f of x, g of x, to x, 0, 0. Does everyone agree? That's how we defined u. So this is what its inverse will do. And we know that it has an inverse by construction. So the last thing I get is x, 0, 0, y plus f of x. And this is exactly what we wanted. We just showed that there's a way to evaluate the function f for whatever input that I want without having any of the garbage bits that we had because we had to introduce some ancilla in order to get the reversible logic gates to do what we wanted them to do. So we can, we know that the 0 registers are required to do this, but we can omit them with the understanding that they're there. So we just showed that x, y can be transformed to x, y plus f of x in a reversible manner. We can note, how would this look in a circuit? It's going to be, we can write it either as a classical or a quantum circuit. It's going to look the same. So x, 0, 0, y. We would first do the unitary, if you'd like, or whatever the reversible circuit is that's doing this. And then we'll have, at this point, x, f of x, g of x, y plus f of x. I should be careful and note that this u only acts on the first 3 registers. The only reason we introduce y is to make a copy of the output that we want. So at this point, we have f of x, and what did we say? It was the second register. So at this point, I would do a C0 gate. And in a circuit, we indicate the C0 gate like this. It's good notation because the circle plus reminds me of what I'm doing. And similar to the Fredkin gate, we use the solid dot to indicate controlled on the control bit being in the 1 state. Okay? So at this point, I have exactly y plus f of x. And then what I do is I just undo this u. So that will be u inverse. And when we do quantum circuits, that will be u dagger.
And then the only reason that C0 is not valid in the no-coding theorem is because it's an arbitrary factor, right?
So it's a great question. So remember, we had the no-cloning theorem from quantum mechanics. That said that in general, we can't make copies of quantum states unless they are orthogonal. Well, in this case, the quantum states that we're using are orthogonal. We're thinking about the 0 state and the 1 state standing in for the bits 0 and 1. And so these two states are orthogonal. We can clone them. Okay, so the last remark to make about this is that we have a universal gate set. Before we were talking about complexity classes, P and NP. So it turns out to be the case that the complexity classes don't change whether you're using irreversible logic gates or reversible logic gates. Why is that? It's because the overhead that we need here, the number of n syllabits and the number of logic gates, will be polynomial. It will actually be linear in the size of the input. You can think about that. Okay, I need 2 copies of the registers here. At most, they're going to be, the size of the output function f and whatever the garbage is. So that's, we're relating that to the size of the inputs. So it's going to be like, 2 copies of that. It's not going to be like, an exponential number of copies or something. So the complexity classes won't actually change whether you're using reversible or irreversible logic. That's important because that allows us to carry it over into the quantum complexity classes.